day, everyone, and thank you for joining us today. My name is Dave Mercer, and I'll be the moderator for our presentation. Our webinar today is titled High Integrity Pressure Protection Systems, or HIPPS, a Process Engineering Perspective. In industrial facilities, careful design of overpressure protection systems is critical to preventing personnel injuries, damage to equipment, and to the environment. Using a high-integrity pressure protection system instead of a traditional pressure-relieving device is becoming more common. However, designing a HIPPS for the purpose requires more than just an instrumented design. It requires several process design considerations. Today we'll join subject matter expert Jonathan Weber and Lexter Gimenez as they explore some of the challenges that process engineers will encounter when using an instrumented system for overpressure protection.
Good day, everyone. For our safety topic, I will present an overview of Safety Integrity Level, or SIL. Many of the terms and concepts that will be mentioned here will be useful in understanding the main presentation. A process hazard is defined as an inherent chemical or physical characteristic with the energy potential for damaging people, property, or the environment. In the chemical process industry, there are hazards present due to the nature of the operations and the materials used, which can often be flammable, explosive, toxic, reactive, or corrosive. Many processes operate at high pressures or temperatures and require large inventories of chemicals to meet capacity requirements. A process hazard analysis, or PHA study, is a structured, systematic examination of a planned or existing process or operation in order to identify and evaluate risks to personnel, equipment, or efficient operation. PHA is performed by a multidisciplinary team through a series of working sessions. The goals of a PHA study are to identify hazards, which were defined in the previous slide as a characteristic with a potential for damaging people, property, or the environment. The initiating events that cause the consequence to occur. The consequences of those hazards. Safeguards or independent protection layers, which prevent the consequence from occurring. And corrective measures, if necessary, to reduce the risk to an acceptable level. There are different methodologies for conducting a PHA study. These include hazard identification or HAZID, hazard and operability study or HAZOP, and what if, among others. One common method for reducing risk to an acceptable level is by providing independent protection layers or IPLs. An IPL is a device, system, or action which can prevent a hazardous scenario from developing to its undesired consequence, and which is also independent of the initiating event and other layers of protection. Examples of IPLs are basic process control, for example, a level controller that maintains the liquid level in a tank by adjusting a control valve on the tank inlet line. Alarms that prompt the operator to take corrective action. Safety Instrumented System, or SIS, and pressure relief devices such as pressure relief valves and rupture discs. A Safety Instrumented Function, or SIF, is an IPL that is independent of the process control loop. A Safety Instrumented System, or SIS, is a set of devices and software designed to implement one or more SIFs. A SIS is designed to bring the process to a safe state when a hazardous condition occurs. A Safety Instrumented Function, or SIF, is a set of actions that protects against a single specific hazard. It includes all the components from the sensors, through the logic solver, to the final actuating device. For example, high temperature readings in a vessel will trigger the automatic closure of a shut-off valve to stop the flow of the heating medium. A SIS is provided for varying levels of risk reduction. If the risk is high, significant risk reduction is needed. If the risk is low, minimal risk reduction is needed. The safety integrity level, or SIL, is a measure of the amount of risk reduction required by a SIF. It is a measure of the required availability and reliability of the SIF. In other words, the chance that a SIF can fail must be smaller as the risk being guarded against is higher. In general, there are no regulations or standards that recommend specific seals for certain process hazards. The amount of risk reduction to achieve an acceptable level is based on a company's risk acceptance criteria. Seal determination is required for each SIF. There are various methodologies for seal determination. These are risk matrix, risk graph, and layers of protection analysis, or LOPA. For this presentation, I will focus on LOPA. LOPA is a risk analysis method to assess the adequacy of IPLs to protect against a hazardous event. It is a multidisciplinary, workshop-based methodology. For each hazardous scenario, the consequences are defined and the target risk is selected based on client-specific risk tolerability criteria. This is an example of risk tolerability criteria. Again, this is specific to the client or operating company. The categories for severity and likelihood shall also be defined by the client. Based on the severity of the consequence and likelihood, the risk category is identified. For example, let's consider a hazardous scenario for which the consequence severity is a disability or injury resulting in leaving work, and the likelihood of the hazardous event is somewhat likely, meaning that it has happened once before at site. Based on this sample risk tolerability criteria, the corresponding risk category is 3. Each risk category, shown here in different colors, has a corresponding value for TMEL, or Target Mitigated Event Likelihood. This is the frequency of the event which would be tolerable. For instance, for the cells shown in yellow, the client may require a TMEL of 1 × 10⁻⁴, which means that the tolerable frequency of the hazardous event is once every 10,000 years. Shown here is an example of a LOPA worksheet. First, the hazardous scenario which is being analyzed and its consequences, disregarding all layers of protection, must be clearly defined. In this example, the scenario is the failure of a pressure controller, which causes the inlet valve of a storage tank to open fully. This would lead to an abnormally high flow into the tank, which could lead to tank damage and collapse, loss of containment, and potential fire and explosion. Once the consequences are understood, the target risk can be selected based on the company's tolerability criteria. For this example, the target risk was determined to be 1 × 10⁻⁶, or once every 1 million years. Initiating events, which could lead to the hazardous event, must be identified. Ideally, this is done prior to LOPA during a PHA study. The initiating event frequency is estimated for each initiating event. In this example, control loop failure is estimated to have a frequency of 1 × 10⁻⁻⁴, or once every 10 years. IPLs are then identified for each initiating event. For this example, one IPL is a SIF that trips the pump and closes the inlet valves to the tank when the tank pressure reaches the high alarm. Another IPL, C2, is a breather valve that will open to release tank pressure. The next step is defining conditional modifiers. These are factors which have an impact on the risk, but which are not engineered devices. Examples of conditional modifiers are potential presence of personnel in a restricted area when a hazardous event occurs, or the presence of fire and gas detection systems. For this specific example, no credit was taken for the conditional modifiers. The total mitigated event likelihood, or TMEL, is equal to the IEF, highlighted in green, multiplied by the probability of failure on demand of each IPL, highlighted in yellow, and the probability of each conditional modifier highlighted in gray. For this example, no credit was taken for the conditional modifiers, so only the values highlighted in yellow and green are multiplied. The PFD of the SIF C1 was determined to be 1 times 10 to the negative 2 in order to give a TMEL that is equal to the target risk, 1 times 10 to the negative 6. In other words, SIF C1 is SIL 2. As you can see on the slide, the value of the TMEL depends on the value of the PFD, or probability of failure on demand, for the IPL. The value is highlighted in yellow. Each SIF has an associated average probability of failure on demand, or PFD average. This is the likelihood that a SIS component will not be able to perform its safety action when called upon to do so. The PFD is related to the safety integrity level, or SIL. There are 4 possible safety integrity levels: SIL 1, SIL 2, SIL 3, and SIL 4. Note that there is a factor of 10 between each level. A higher SIL corresponds to a lower probability of failure on demand, and therefore a greater availability and greater protection against risk. The risk reduction factor, or RRF, is the inverse of the PFD average. Say, for example, you want to reduce risk from once every 10 years to less than once every 10,000 years. That means a risk reduction factor higher than 1,000 is needed, and you need SIL 3. A SIL 1 system must meet a minimum availability requirement of 90%. The minimum availability requirements for SIL 2, SIL 3, and SIL 4 are 99%, 99.9%, and 99.99% respectively. SIL 4 is almost never used in the process industry, and it is mostly associated with the nuclear industry. Here are a few key takeaways. Risk is a measure of consequence and likelihood. An independent protection layer, or IPL, is any independent mechanism that reduces risk through control, prevention, or mitigation. A safety instrumented function, or SIF, is an IPL that is independent of the basic process control system. It is designed to bring the process to a safe state when a hazardous condition occurs. A safety instrumented system, or SIS, may be comprised of a single SIF or multiple SIFs. The safety integrity level, or SIL, is a measure of the amount of risk reduction that is required by a SIF. For more information on safety instrumented systems and layers of protection analysis, you can refer to previous Innovations Builders webinars on these topics. Recordings of these and other past Innovation Builders webinars can be found on Fluor's official YouTube channel. Thank you for your attention. I'll now turn the presentation over to Jonathan.
Thank you, Lexter, and good morning. I will begin with an overview of the traditional approach to overpressure protection, and specifically the role of instrumentation plays in this approach. We will then discuss various aspects of high-integrity pressure protection systems, or HIPPS, designed from a process engineer's perspective. We will then move on to some special considerations in determining the SIL rating for HIPPS. The purpose of overpressure protection is to ensure that during credible upsets, the pressure does not exceed code-prescribed limits. The allowable factors are prescribed by codes such as the American Society of Mechanical Engineers, or ASME Section 8. Failure to adequately protect against overpressure can result in damage to equipment, people, and the environment. Typical credible scenarios are described in the American Petroleum Institute's API 521 and include, for example, pool fires and maloperation of valves. This assessment of credible upsets is a key activity in the design phase of a project. Each plant will typically have some unique aspect that requires an assessment of the system as a whole to understand how the systems interact and respond during the upset. Credible scenarios often follow the rules of double jeopardy, where two independent upsets are not considered credible. Care is required to not rush to conclusions in regard to double jeopardy. A careful assessment of latent or hidden failures that can exist for extended periods of time or dependencies between different upsets is necessary. We can broadly categorize several different approaches of overpressure protection. For centrifugal pumps or compressors whose pressures are self-limiting, it is desirable to select a design pressure higher than the maximum developed pressure when the pump or compressor is blocked in. Pressure relief devices are used when the pressure is not self-limiting or the self-limiting pressures exceed the design pressures, as you see occurring in brownfield tie-ins. Note, for simplicity, I will just use the term pressure safety valve or PSV going forward, but of course other devices can be used such as rupture discs. If a pressure relief device is not practical, but there is sufficient time for operator intervention and adequate operator training, then credit can be taken for operator intervention to mitigate the event. For example, to close the feed valve to prevent overfill when the liquid reaches a high level. If a pressure relief device and operator intervention are not practical, instrumented overprotection systems, also known as HIPPS, can be used as the last line of defense. Pressure relief devices are still the traditional method and generally favored by codes for overpressure protection. We will next briefly expand on the use of pressure relieving devices. The traditional method of overpressure protection is via a PSV. The figure on the left is a simplified schematic of a bellows-type spring PSV. The spring exerts a downward force to keep the PSV closed until the inlet pressure reaches the set pressure. At this point, the disc begins lifting, and with an increased overpressure, the disc is fully lifted and the flow through the PSV to the outlet is determined by the nozzle area and the pressure difference across the valve. In this example, a bellows is used to shield the top of the disc from back pressure at the valve outlet. This is to help reduce the effect of back pressures on the opening of the disc. API 520 has details about the different types of relief valves and their function. The orifice is sized based on the estimated required flow to relieve the overpressure. The fluid characteristics such as phase, liquid vapor or two-phase, density, temperature, etc. are used to determine the minimum required orifice area. In addition, special care is given to both the inlet and outlet piping sizing to ensure adequate performance. By ensuring the relief device can pass the required flow, the PSV provides a mechanically self-actuated device that can prevent overpressure by diverting the excess flow to a safe location, typically a flare where the gases are safely combusted. The following simple example is just used to illustrate the basic function of a PSV during an overpressure upset. Here is a simple two-phase separator. The feed flashes and vapors are removed via the control valve at the top of the vessel, and the liquids are removed via the bottom. The two-phase separator under normal operation operates under mass balance. The mass of liquid and vapor leaving the vessel is equal on average to the mass flow in. In this example, the feed supply pressure is 4,000 kPa(g), but the separator is designed for 3,000. Since the feed supplying the pressure can exceed the design pressure of the vessel, then overpressure protection is required, for example, to protect against the closure of the vapor control valve. A PSV is provided with a set pressure equal to the design pressure in this case. Here we see the vapor control valve is closed due to some failure or maloperation, and the pressure will begin to rise. Without overpressure protection, the pressure would continue to rise towards 4,000 kPa(g). When the pressure reaches 3,000, the set point, the PSV will begin to open. Per ASME code, a further pressure increase of 10% is allowed in this case. The orifice is sized to relieve the incoming vapors with some consideration of the flash conditions at the relieving pressure. Next, we will discuss the traditional role of instrumentation in the overpressure protection with the PSV. Control actions, DCS or SIS, are not credited when determining the required relief load to be passed by a PSV. If a control action reduces the required relief load, then the action is assumed not to occur. However, if the control action makes the relief load larger, then it is assumed to occur. To demonstrate this, consider the following example. We have a pressure control and flow control combination, typically seen in a storage facility where the pressure controller will direct excess flow to storage, for example. This pressure control valve might be open or closed during normal operation depending on the feed flow rate and the rate drawn by the flow controller. In this case, a PSV protects the system downstream of the flow controller. If this line is blocked in, the PSV will be required to relieve the flow to prevent overpressure. In this example, when it's blocked in, the flow controller will tend to open, increasing the relief load to the PSV when the line's blocked in. Therefore, it is assumed the flow control action occurs. However, the pressure control valve will also tend to open, thereby reducing the relief load. It is assumed this control action does not occur. We would assume that the pressure control valve is in its last position before the upset. If credit is taken for this diverted flow via the pressure regulator, then careful consideration of turndown operation is required if this flow is credited. If there is consideration of a PSV on the pressure controller rundown, then if that line were blocked in, the flow control valve would tend to pinch to maintain flow. We would assume this occurs. The pressure controller would tend to open to increase the relief load. We also assume this occurs. Since in one case you are claiming the pressure control valve opens and in the other case it takes no action, this is sometimes perceived as speaking out both sides of your mouth, but it is important to understand the assumed control action is relevant to the specific upset and relief valve under consideration. So the PSV is sized to provide the last line of defense. There's no credit for any instrumented action. The PSV is selected to provide the best possible reliability for the given service. It's mechanically self-actuated with no reliance on the instrumented system for the PSV to function. The PSV still provided regardless of the reliability of other instrumented systems. Next, while a PSV or rupture disc is still the traditional method of overpressure protection, in certain cases, a PSV may be impractical. For example, due to a very large liquid load to the flare, which would require an impractically large effluent handling system, or for certain services. We have seen examples where the traditional design would have been impractical, for example, to prevent overpressure due to overfill of a propane storage vessel fed by several high-pressure pipelines. The flare system was not designed to receive such a high liquid load. HIPPS offered a practical and cost-effective means of preventing overpressure in this case. In cases like this, HIPPS can avoid costly re-rating or reconfiguration of flare systems. Typically, the HIPPS actually prevents the overpressure from initiating by closing off a high-pressure source. It thereby also avoids the release of materials to the flare and limits damage to equipment. For example, a pressure relief device on a column may result in internal damage due to a high vapor loadings during relief. The term HIPPS used in this presentation is limited in a specific sense to refer to an instrumented protection system that is the last line of defense to prevent an overpressure event. The HIPPS makes the overpressure non-credible in terms of its probability of occurring. This may result in the pressure relief device or PSV being removed. Or the specific case could be removed as a credible scenario for the pressure relief device. It may also reduce the required load for the PSV. HIPPS with 2 Ps versus HIPPS with 1 Ps is not always used consistently. The IOGP, International Association of Gas Producers, define HIPPS with 1 P as a general protective system and HIPPS with 2 Ps as dedicated to overpressure protection. Other terms might be overpressure protection systems. The use is not always consistent, but in this presentation and talk, the intent is to refer to HIPPS with 2 Ps as an instrumented system that replaces or reduces the load on a PSV and effectively becomes the last line of defense. And next, we talk about current regulations. So current regulations tend to be pressure relieving device centric, likely due to their self-actuating nature and independence of instrumented systems. As such, they make an effective last line of defense in many cases. For example, the Canadian Pressure Vessel Code states the following. HIPPS would fall under other means. Some local jurisdictions require a pressure relieving device or other means are accepted only upon approval. They may require a justification for why a PRD or pressure relieving device cannot be used. Even though economic and schedule are intimately tied to practicality, some jurisdictions may not be swayed by purely economic and schedule considerations. It's always better to frame the opportunity for HIPPS in terms of impracticality. There are several different stakeholders when implementing a HIPPS. Some jurisdictions may have specific requirements for a minimum acceptable sill rating. Some may not have any specific requirements. The owner internal risk tolerance will play a role in determining the sill rating of the HIPPS, and the owner must be aware and committed to maintaining and testing the HIPPS system. In addition, the engineer of record must apply due diligence and meet generally recognized acceptable good engineering practices. If a HIPPS system is planned, it is best to engage all stakeholders to align on expectations. This should ideally be worked out conceptually in FEED to help avoid delays later in the project. Here is a typical SIL 3 configuration. The HIPPS is activated by a high alarm on the pressure transmitters. A 2 out of 3 configuration requires 2 transmitters to alarm high before the logic is initiated. This helps reduce spurious trips that would occur if only a single transmitter were used. It also helps improve the reliability since a failure of a single transmitter does not prevent the HIPPS from functioning on demand. Transmitter valves can be interlocked or controlled to ensure never more than one device is taken out of service. The final elements, 2 emergency shutdown valves in this case, are used in a 1 out of 2 configuration, which means that one of the 2 valves must close to prevent the overpressure, i.e. closure of one valve is sufficient to be successful. In this case, it is cleared by cutting off the source of overpressure, i.e. the upstream flow, before the overpressure occurs. The HIPPS avoids having to relieve material to the flare, which avoids emissions during an upset and avoids modifications to the flare effluent handling systems. While convincing hallway arguments might be made to argue a HIPPS system will functionally prevent an overpressure, more effort is usually required than an intuitive acceptance. Typically, a dynamic model is developed to verify the HIPPS can prevent the overpressure. This dynamic assessment is also critical to determine the available response time available. This is the time between the initiating variables, for example, pressure, reaching the expected alarm point to when the overpressure event will occur. The available response time is not the time it takes from the initiating event. Rather, it is measured starting from the time when the initiating variables reach their set point. It must account for process lag. The control system's review of the actual response time will account for sensor response times, solver logic time, and final elements to reach their safe state, typically the time for an emergency shutdown valve to close. The alarm points might be adjusted to provide more response time, but consideration of the operating margin and disturbances is important. Note that a ruptured disc and PSVs tend to react relatively very quickly. It can be a challenge to ensure the HIPPS systems act quickly enough to prevent the overpressure. The response time of all of the components in the HIPPS must be considered. I want to be careful to distinguish crediting other instrumented systems in terms of function versus reliability. Improving the functionality, by which I mean the demonstration that the HIPPS alarm points and final actions are sufficient to prevent overpressure, should not credit the function of other instrumented actions. The HIPPS must be able to function and prevent the overpressure independent of the actions of other control functions. This is similar to the traditional design assumptions we described earlier with the PSV. However, a unique aspect of HIPPS is that the reliability does sometimes credit other instrumented systems. We will discuss this aspect a bit more further later. Some additional comments. In evaluating the functionality, we should consider if leakage through an emergency shutdown valve will have an appreciable effect on overpressure. For example, if fuel gas valves to a fired heater are closed, we need to consider the residual heat in the refractory or leakage of steam through an ESD valve to a steam reboiler. Note that the HIPPS should be independent of other instrumented systems, so separate initiators from the DCS and SIS are recommended. For example, if level transmitters are used, a separate bridle may be required to prevent common modes of failure. For the initiating variables, it is sometimes assumed that they must be pressure. Other variables may be more suitable to function as initiators, as we will see in the following example. A well-designed HIPPS can be rendered ineffective if the installed elements do not meet the required specifications. This can occur for example, during a squad check or during field replacements of an initiator or final element. It's strongly recommended to document these critical performance requirements on the individual data sheets. The dynamic assessment and assumptions required will depend on the configuration of the HIPPS. It will depend on both the initiating and final elements selected. Some choices are better than others. A good design should support an analysis with a minimum of complicated modeling and assumptions. Here is an example where the choice of the initiator had a significant impact on the functionality of the HIPPS. This is an example where if liquid overfill occurred, the resulting large liquid relief was impractical to handle. A HIPPS was selected to prevent liquid overfill since there was insufficient time to credit operator intervention. It was proposed that pressure transmitters will provide an indication of liquid overfill. The argument was made that as the liquid rises, the vapor space compresses, and therefore the pressure will be a measure of the impending liquid overfill. It is critical to assess situations where the proposed HIPPS system will not function. To validate the functionality of this concept, the assumptions would have to be made regarding the fill rate, heat transfer coefficients, ambient conditions such as temperature and wind speed. As a result, the predictions by the dynamic model would only be as good as the heat transfer coefficients or other assumptions. Some concerns with this approach are also raised. The rate of pressure rise is a function of fill rate. A slow creeping fill rate can allow temperatures to equalize with ambient with no observable pressure rise. If a pressure controller to flare was present, it would open and remove any pressure to level correlation. Predicting how fast the pressure rises upon the instantaneous moment that the liquid overfill occurs is even more complicated and not worth attempting. While the pressure transmitters may have been easier to install, upon review and assessment, it's clear that using level transmitters as the initiator would provide a more robust, simple HIPPS design. An important consideration is that the activation of the HIPPS may result in other consequences outside the unit being protected. HIPPS frequently closes a valve or trips a pump, for example. This can have consequences to both upstream and downstream units. This can result in a single contingency localized failure expanding to other parts of the plant. For example, a HIPPS event could also result in reverse flow when it trips a pump discharging into a common header. These knock-on effects can impact flare sizing and should be considered. In liquid pack systems, there are additional considerations. The fast closure of an emergency shutdown valve or tripping of a pump can result in hammering or transient pressure waves. This can require specialized assessment to ensure protection against transient pressures. An interesting trade-off arises due to the HIPPS favoring fast closing valves and transient protection favoring slower closing times. Let's summarize and contrast the traditional approach with HIPPS for overpressure protection. These are general statements. I'm sure there would be some exceptions to each of them. A key difference here is in regard to the reliability of the final layer of overpressure protection. ASME 13 does not specify a minimum sill rating for the HIPPS. In some cases, the local jurisdiction does not provide any specific guidance on a required minimum HIPPS sill level. The guidance provided in API 521 is informative. It is also to note the use of the word risk, which suggests the consequences can be considered. API has traditionally supported the consideration of consequences, a classical example being consideration of exceeding the hydrotest pressure during a tube rupture. While a lower sill or reliability favors cost and maintenance testing requirements, the remainder of this discussion will focus on some potential pitfalls when determining the sill rating for HIPPS. Let's begin by considering a hypothetical LOPA example. By crediting a probability of failure of 0.1 for a BPCS action, an SIS action, occupancy, and ignition, with an acceptable target frequency of 10 to the minus 5, we can see that the HIPPS reliability has been rapidly degraded to a non-sill rated system. I've never actually seen a non-sill rated system for HIPPS be proposed. However, this is simply meant to illustrate how common credits in LOPA can rapidly degrade the sill rating of the HIPPS. Since the HIPPS is providing a regulatory function by replacing a PSV, which is mechanically independent, as the last line of defense, it is worth critically investigating the various credits used to reduce the reliability of the HIPPS. Let's look more closely at some of the credits used to reduce the sill rating. Let's start with the credit using a BPCS action in the DCS to prevent overpressure. Is this appropriate? In many cases, I doubt the DCS is fast enough to prevent overpressure. Has the functionality of the BPCS function been validated? Has the potential for different tuning parameters been considered? Are the set point and tuning parameters adjustable, or have they been locked as safety critical items? Could the controller be on manual? Of course, it is essential that as an independent protective layer, that any upset that leads to the overpressure does not also lead to a failure of that specific BPCS function. It is possible the BPCS credit, while permissible, is not appropriate for credit, often appropriate for credit and overpressure protection. Similar considerations are required to validate the functionality of the SIS function. What about mitigating factors like occupancy and likelihood of ignition? This is where things get interesting. ASME states that the HIPPS must make the overpressure above co-prescribed limits non-credible or unlikely enough. ASME does not consider the likelihood of the consequence of overpressure. It doesn't matter to ASME if an operator is nearby the wind direction, if the vessel ruptures, or an ignition source is present. From a strictly regulatory point of view, credit for things like occupancy and ignition do not appear appropriate or consistent with the ASME requirements. The reliability of the HIPPS can be very quickly reduced in a LOPA. A careful assessment of each credit in LOPA is required. Has the functionality being validated? Is the LOPA credit consistent with regulatory intent? There is a general practice or consideration that the HIPPS should be at least as reliable as the PSV it's replacing. It has been suggested by Lawley and Klutz that the PSV should be 10 times more reliable than the HIPPS. That the HIPPS should be 10 times more reliable than the PSV, since a failed PSV can still partially open and provide some degree of overpressure protection, whereas a HIPPS failure tends to result in no action taken to prevent the overpressure. There is a complicating factor here, since there is such a wide range of PSV reliability claimed. It depends on the valve type and the service. For the purpose of LOPA, the reliability of a PSV might be conservatively low to ensure additional safeguards are provided during the LOPA. However, this is not conservative when using this basis for comparison as to the target the HIPPS should satisfy. In some cases, a PSV is being used a HIPPS is being used because the PSV is inherently unreliable in the given service. Making the argument that the HIPPS only needs to be as reliable as an unreliable PSV is not very convincing. Some other considerations to be aware that a certain cell performance covers a range of performance. it is not recommended to round down the risk reduction factor. There's a significant difference in reliability between a SIL 3 with a RRF of 1,000 versus 10,000. This, of course, is a general rule applicable to all SIFs. We should note that the CCPS states that most HIPPS are generally expected to achieve SIL 3. Several other references also state the typical HIPPS are between SIL 2 to SIL 3. Does this represent a recognized and generally good, acceptable engineering practice? So in summary, HIPPS are complex. They should not be used lightly as a replacement for the PSV. You require good justification for the use of the HIPPS to replace a pressure relieving device. Caution is also required in LOPA when determining the SIL. There are several considerations that must be balanced. Each design and client and regulatory environment is unique. And I would like to share some concluding thoughts. When a HIPPS replaces a properly sized PSV, it becomes the last line of defense against overpressure. While most HIPPS do end up being SIL 1, SIL 2, or SIL 3, in some cases a LOPA may conclude that a SIL 1 is sufficient. While I have not actually seen a HIPPS proposed with a non-SIL rating, it is mentioned here as a theoretical curiosity to highlight the question. Is there a minimum required SIL rating for HIPPS? Prescriptive regulations on the minimum HIPPS reliability are not currently present under ASME. However, some local jurisdictions may impose a minimum SIL requirement, many may not. The common term last line of defense invokes a feeling that there might be something special about this layer, perhaps being held to a higher standard of reliability. I doubt if cheaper PSVs with a claim of a higher probability of failure and demand will ever be marketed. But if they were, do we believe codes like ASME would allow the use of these valves as a last line of defense? There are differences of opinion if a SIL 1 or non-SIL rated HIPPS is appropriate. Every case is different and requires a careful review of the credits taken and to balance regulatory requirements with good engineering judgment. The right answer to me is somewhere between code and an assessment that considers consequences. In the extreme, strict application of ASME requirements can result in some funny requirements. For example, a PSV with zero relief load when the potential overpressure is less than 10% is installed. Or, even worse, a PSV is installed when there is no source of pressure that can exceed the design pressure. These examples represent the extreme compliance with ASME code and provide no safety benefit. On the other hand, a risk-based approach can result in a very low SIL rating for a HIPPS for hazardous systems if credits in the LOPA are generously applied. If the unmitigated upset didn't exceed hydrotest pressures, personally I wouldn't be overly concerned regarding the SIL level of the HIPPS. However, I would recommend a close investigation of a SIL 1 HIPPS applied to a system whose unmitigated consequences are extremely hazardous. And this concludes my talk, and I want to thank everyone for attending. And with that, I would like to hand the discussion back to Dave.
All right. Thank you very much, Jonathan. That was great. So I can see we have a few minutes left before the top of the hour, and we'd like to take this remaining time to ask Jonathan and Lexter a couple of questions that we've received from the audience, and we have had a very large number of attendees on the call, so we have the questions streaming in here. So Jonathan, I'm going to come to this one. Can HIPPS and PSVs complement each other for a comprehensive process safety strategy?
Yes, absolutely. In one example, you sometimes, due to leakage through the HIPPS valves, you required to put a smaller PSV downstream to account for that leakage. So the upstream HIPPS in that case is severely reducing the required relief load on the PSV, and together they function to prevent the overpressure. The other case we see sometimes and see it happening more often is that a PSV is not sufficient. It's sufficient to meet code compliance, but it's not sufficient to meet client risk tolerances. So while you may need additional instrumented systems to close that gap and meet the client risk tolerances, from a regulatory point of view, those instrumented systems are not necessarily replacing the PSV or reducing the relief load, so they're not in a regulatory sense HIPPS, but they're a critical part of an instrumented system working in conjunction with the PSV to meet client risk tolerances.
All right, very good. The next question that's come in here, are there cases when a HIPPS system is used for scenarios other than to replace a PSV?
Yes, well, because we see them also to reduce the required relief load on the PSV. But I think maybe the question might be expanding a bit beyond the specific use of the word HIPPS that I've used in this context. So I've used the words HIPPS specifically to refer to instrumented systems that are used to replace the PSV or reduce the required relief load, and in that regulatory sense. But as I said, the use of HIPPS with 1P, 2Ps is used broadly, and it's not always consistent. There are always other functions, safety functions besides overpressure, that can require the consideration of a high integrity protection system. If it's not used to credit the relief load on the PSV or remove the PSV, it's not a regulatory HIPPS, but it's a HIPPS perhaps with 1P in its own sense. There's other safety instrumented functions required to reduce risks other than overpressure that can end up being high integrity.
Right. Okay, very good. Well, thanks for that response. We'll move on to the third question here. A little bit more subjective, but what do you think's been driving the increased use of HIPPS in industrial facilities? Any thoughts on that one?
I think that there's several factors. One is an increasing comfortableness with the technology as the last line of defense. And I also think, though, many, like for example, refineries built several years ago have gone through several layers of debottlenecking and expansions. And as such, they'll eventually hit and have hit that limit on the flare capacity. So it becomes impractical to completely debottleneck an existing flare handling system, and the HIPPS in these cases can offer a practical solution to help reduce the load on the flare system or to reduce the required relief loads.
All right, excellent, thank you. I like this question because we commonly get questions from our industry colleagues and clients in relation to cost. So I'd like to pose this one to you. How does the cost of a HIPPS system compare to the cost of a PSV?
Without getting into specific costs, generally the HIPPS systems are more expensive than the PSV. However, in many cases you are installing the HIPPS only because the PSV is ineffective, so there's not an option. That's you have to go to the HIPPS. But the other cost side of the cost is the cost that it would be to the impracticality of expanding an existing flare system, which in many cases, every case is different, but in many cases, that cost of debottlenecking the system would far outweigh the cost of a HIPPS.
All right, excellent. Lexter, I'm going to ask you, how is the probability of failure on demand related to time, such as the number of years in operation in typical process industries?
Yes, so there was a question regarding the PFD and whether it is expressed in number of years. So to clarify that point, PFD is a probability and it is not expressed in years. During the safety topic, years were mentioned, but it was not used as the unit of measure for PFD. it was actually used as the measure for risk or likelihood. So in the example that I gave, the initial risk was once every 10 years, and we want to reduce it to once every 10,000 years. So for this example, the equivalent PFD is 1 over 1,000, or 1 times 10 to the negative 3.
All right. Thank you, Lexter. Jonathan, I don't know if you have any other comments to add to that.
Just maybe a couple small comments. I think when you talk about high demand versus low demand, there is a difference in the term of probability of failure per hour, I believe, if you go to a high demand system. How the actual average probability of failure of demand is calculated, I would have to refer back to our functional safety experts to get a really detailed answer on that. I know it's complex, and I think that might be best suited for a written response with some clarifications from our experts in the functional safety group.
Okay, very good. I think we have time just to squeeze in maybe one or maybe two more questions here. So Jonathan, I'll come back to you on this one. Can a HIPPS system provide protection against surge pressure or water hammer in pipelines?
Okay, that's a really good question. We have seen it done, yes. However, it's very, very tricky because of the extreme speed of the pressure transients. So yes, it can be done, but there are other alternatives the first preference is always to try to slow down the speed of the valves closing, or to put some sort of buffer on the pressure, like an expansion tank. And there's also specialty valves designed, like Danfold valves, specifically designed for surge. But it can be done, but I would caution that it's only used as a last resort because it becomes very, very complicated. Proving the functionality with the very high-speed waves is very complex and requires very specialized assessment. So I tend to prefer to avoid HIPPS on liquid pack systems where possible.
Okay, very good. And I'm going to squeeze one last one here in, Jonathan, and it's non-technical in nature, but I think the audience would appreciate your perspective on it. And it's this. Is there any advice that you may like to provide to younger engineers considering a career in process safety?
Sure. I think it can be a very rewarding field to study. It's rich in both the depth and broadness, that you have to assess units not only in their normal operation, but in their upset conditions, and comply with codes and many regulations. And I think one of the, somebody that's passionate about safety, it's a great career. But I think one of the most important pieces of advice I've learned over the years, and that maybe is worth sharing, is that, you can be gung-ho and very passionate about safety and be very strict in interpretations, but having some flexibility and appreciating that there's many different interpretations of code, many different risk tolerances, and change how you discuss these options to reflect that you appreciate there are other opinions on the matter, certainly helps get your position across, as opposed to being too hard line on a certain stance.
Yeah, that's really good advice. No, that's great. Great advice, Jonathan, and we appreciate your perspective and all of the years of experience in this discipline that you're bringing to the conversation here today. So it does look like that's all the time we have for questions today. And I'd like to thank you again, both Jonathan and Lexter, for what I'd call a very informative webinar, and also in the time that you've spent both today and in preparation for today as well. I'd like to thank our audience for attending today, and it certainly has been a pleasure being your moderator. So please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com, or following our social media channels using #InnovationBuilders. If you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. Once again, we appreciate your attention and thank you again for dialing in today. We will send out a compiled list of the Q&A shortly, along with a notification that the webinar recording is available for replay on fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will certainly get back to you. From all of us at the Innovation Builders team, have a wonderful day, and thank you.